Hello there and welcome to the series of videos going through the content of A-level maths. Here we're doing an extra video on the drawbridge type problems that we have seen in past papers but we've not seen so much in the textbook, so here's a bit of an extra resource for these types of problems. These problems here belong within the chapter of moments, so we're going to be taking moments and potentially resolving forces upwards and downwards. So in this question here we have a rod that's horizontal and a piece of string that attaches point B to point C here, and an extra small block here that's of mass 3m, and the rod here is a uniform rod with mass m, and the angle alpha is represented by tan alpha equals 3/4. So I think I'll deal with that bit first then. Put the alpha down here, it's opposite over adjacent for tan, so therefore the right angled triangle by Pythagoras will give me a 5 up there, so therefore sine alpha will be 3/5 and cos alpha will be 4/5. Great, okay, so let's move on to the question then. We want to, using the model, shown that the tension in the rope is this expression here. So as I say, this topic here belongs within the topic of moments and resolving forces. So what we're probably going to do here is add on the forces onto the diagram first before we evaluate which strategy we're going to use. So the first things first is that there is tension in the rope, and the tension will be going upwards, and that is to provide support for the beam in the upward direction. The rod is also a uniform rod with mass m, so therefore there is a force of mg. The small block P also has a mass of 3m, so therefore has a force of 3mg. Now, thinking about the point A here, there's no pivot here, there's no glue that's sticking this rod to the wall here. All we're told is that it's a rough vertical wall, and whenever you see the word rough, triggers should be going off in your brain thinking there must be friction at some point on this wall. So there's going to be friction either acting up the wall or acting down the wall, and we've got to think about which direction it's going to be. Thinking about the rod, if there was no friction, it would just slide out from underneath, it would travel downwards. So therefore friction will act in the opposite direction to balance out that downwards movement that would happen otherwise. So friction acts upwards here. And to work out friction we use F equals mu r, so we're going to need an R calculation in there at some point, or an R force in there at some point, and that will be the force here. It will be a force R that's going outwards from the wall onto the plank. So it will be directly at the intersection point of A. I've drawn it slightly below just so that my arrows don't get kind of crossing over with each other. So there's a force R, a reaction force between the wall and the beam. Okay, so now we can evaluate which strategy we're probably going to use. Can we resolve forces upwards and downwards, or should we take moments about a certain point? I think there seems to be a lot of things happening at this pivot point A here, not the pivot point A, but the intersection point A here. I think what would probably be safer is if we take moments about this point A here. So taking moments about A. When we take moments about A, this friction force here and this R force here will not be required in my formula because they are a distance 0 away from this point A. So let's have a look at the clockwise moments and setting them equal to the anti-clockwise moments. The first moment, or the first force that we'll consider, is this mg force here. It's a force mg, distance A away from the pivot point, so therefore its moment is going to be mg times A. And that's going to be on the clockwise direction, because if we consider this red point here to be the centre of the clock and it travels downwards and to the right, that's in the clockwise direction. The next force that we'll consider here then is the 3mg force here. That's going to be travelling in the same direction as the previous force that we've used. It's a force of 3mg and a distance x, so therefore the moment here is going to be 3mg times x. Considering the final force that's going to go on the other side here, and that is tension. So because this force here is acting at an angle, we actually need to resolve it So it's perpendicular to the distance that we are working out. It's a distance 2a, so that's fine. We need to now work out the size of this force here. Well, I think it would be useful to note that this angle here is 90 minus alpha, so therefore this force here is going to be t cos 90 minus alpha. And remember, you can always write cos of 90 minus alpha as t sine of alpha. And that would also make sense if you imagine your force is actually this vertical line here, where the wall is, then that's effectively opposite to the alpha angle there. So t sine alpha will be this force here. So t sine alpha times by the distance of 2a will be the moment on the right hand side. Let's now go ahead and simplify the left hand side, and we'll also bring in sine of alpha as the value 3 out of 4. So there we are. So 3mgx plus mga equals 2a times t times 3 out of 5 for the value of sine alpha. So we've got to rearrange it into this thing here. I'm going to do it all in one go, but you can see how this would work. Factorise out mg from the left hand side first, times up by 5, divide through by 6a, and there you have it. T equals 5mg brackets 3x plus a all over 6a. So there we are, that's answer to part A. So moving on to part B then, the magnitude of the horizontal component of the force exerted on the plane A by the wall is 2mg. Now what does that mean? Let's reread it. The magnitude of the horizontal component. So horizontal force we're thinking then, if it says horizontal component, I'm thinking that this is what they're referring to here. They're thinking about this R force here. The force exerted on the plane A, AB rather, by the wall is 2mg. Yeah, that makes sense. It's the force exerted onto the beam by the wall is 2mg. Lovely. So we'll rewrite R as the value 2mg. Find x in terms of A. Okay, well what we'll probably do here then is we've got another strategy that we can use, which is resolving horizontally. We could resolve vertically as well, but that won't take into account this 2mg force, the extra bit of information they've given us. So we're going to be resolving our forces horizontally now. So rightward forces will equal leftward forces because the plane is not moving. And the only two forces that we have moving left and right, or acting towards the left and right, is the R force that's acting to the right, and also the T force that is partially acting to the left. We'll have to resolve it first. So in this case here, we're going to set rightwards forces, that's R, we'll replace that with 2mg in a second. We'll balance out with T cos alpha, so it's going to be the force that's travelling along in this direction here, that's the cos component of alpha. So, substituting in t, we've found the value for t earlier, so that will get replaced. R will get replaced with 2mg. So substituting in both of those expressions there, we're going to have 2mg on the left. We're going to have 5mg brackets 3x plus a all over 6a on the right, and times by cos alpha. And if you remember from before, cos alpha is equal to 4 out of 5. And now we'll have to rearrange. Now what we can see here is that we've got mg's on both sides here. We've got a 5 on the top and the bottom of a fraction here. We've got 2 on this side here, and that will partially cancel out with the 4 over there. So we have here, before we cancel out the 2, 2 equals 4 brackets 3x plus a all over 6a. You can see what will happen here now. We're going to times up by 6a, so that would be 12a, divide through by 4, so that would now be 3a equals 3x plus a, and then we end up with a final answer here of x equals 2/3 a once you've rearranged this from here to here. Okay, so there we are, we've found x in terms of a, and the way we've solved that is by resolving the forces horizontally. Right, so moving on to part C here, we have the forces exerted on the plank by the wall acts in the direction that makes an angle beta to the horizontal. Find the value of tan beta. Well, what forces are exerted on the plank by the wall? We have the friction force here, and we have the 2mg force here. So what's going to happen then is with these two forces, we're going to have a total vector that's taken into account both the friction force and the 2mg force. And what I imagine they want us to work out is this value beta down here, that is the angle between that total component of these two forces here and the horizontal. So what we need to do then, we've got the horizontal, we now need the vertical component here, that's friction. So we need to work out the value for friction. And the strategy we're going to use there is to resolve forces upwards and downwards. We're going to have friction plus t sine alpha in this case, because that upward direction would be opposite the angle alpha. And we're going to have 4g going downwards, so it's going to be friction plus t sine alpha equals 4mg. So now what we're going to do is we're going to replace t with what we know t to be, and inside the t equation here we're going to replace x with 2 over 3a. Now you can imagine what's going to happen here. If we have 3 times 2 over 3a, this whole component here is going to simplify to 2a, so this whole part inside the bracket here will actually all simplify to 3a. So watch 3a appear in this formula here. It's going to be 5mg times by 3a all over 6a times by sine alpha. And remember from before, sine of alpha was 3 over 5. And then we'll have plus friction on the left-hand side and simplifying the mg plus 3mg to 4mg on the right-hand side. So now we need to work out the value for friction. We're going to need to take this big component here, simplify it and move it all onto the right hand side. First thing we'll do is probably cancel out the a's and cancel out the 5's from here and here. Now let's simplify and move everything onto the right hand side. And once we've tidied everything up there, both have a common factor of mg, so it's going to be 2.5 mg on the right hand side there. So we've now got friction equals 2.5 mg. And let's now make that triangle that I was referring to earlier. We're going to have 2 mg along the base, 5 over 2 mg on the height, and it's going to be the angle after these two components are combined into one single force vector to the horizontal. So it's going to be a tan calculation here to work out the value for tan beta. It's going to be 5 over 4, mg's will cancel both out, and it's going to be opposite over adjacent. So 5 over 2 over 2, that's 5 over 4. Okay, so moving on to the last part here, the rope will break if the tension in it exceeds 5 mg. Explain how this will restrict the possible values of P, and you must justify your answer. So now we know that the tension here cannot be any bigger than 5 mg. So what we can do then is make an inequality that says that the tension has to be less than 5 mg, or less than or equal to actually. So the tension must be less than or equal to 5 mg. And what we should be able to do now is by cancelling mg's from both sides, mg is definitely a positive value here, we should be able to work out an inequality in terms of x and a. So cancelling out 5's from both sides as well, maybe timesing up by 6a onto the other side. And eventually, once you've rearranged enough here, you're going to get x is less than or equal to 5 over 3a. Now what could we conclude about this? Well, the total length of A to B is 2A, or in other words 6 out of 3A. So what we're saying here is that the small box P, or the small block P, can't be in the final 1/3 A portion of this beam here, or it can't be in the final 1/6 portion of the beam in total. Okay, so there we are. That's how we answer these types of questions here. Now, generally, just thinking about this point P here, in this question, it was phrased in such a way that it wasn't glued onto the beam and the wall weren't glued together, or they weren't pivoted by a pulley or a pivot point or anything like that. If it is a type of question where it's a pivot point here, then all the same maths is going to apply. You're just going to have a force that's being applied to this pivot point here, and you can then break that force into a vertical component and a horizontal component. So exactly all of the maths would work exactly the same there, as if I had a pivot point to if I didn't have a pivot point and I just had a rough wall. Okay, so your turn to have a go at this question here then. Pause the video and try this question out. Right then, let's give this one a go then. So a uniform rod AB of length L and mass m kilograms rests one end touching a rough horizontal wall. The rod is kept in equilibrium by a light inextensible string AC, where C lies on the wall directly above B. The plane ABC is directly on the wall, and the angle BAC is alpha, where tan of alpha is 5/12. So let's deal with that bit first. That angle there is alpha, and let's sort out the other types of angles here. We're going to have 5 on the opposite, 12 on the adjacent. So sine here, the other side is 13. Sine alpha is 5/13, and cos of alpha is going to be 12/13. Great. Find the tension in the string, or show that the tension is 13/10 mg. So the tension is going to be acting this way here. We have a uniform rod of length L, so we know it's going to be a distance L/2 from point A or point B, given that it's going to be in the centre, and it has a mass mg. So it rests with one end touching a rough vertical wall. So we're going to have one side that is friction, and friction is going to be acting upwards because if friction wasn't there, the most likely situation is that point B is going to slide downwards, so friction will be acting upwards in the opposite direction there. And we're also going to need a reaction force coming outwards here, so we can then use F friction equals mu r. So let's give it a go then. Show that the tension in the string is 13/10 mg. Now the strategy for doing this question here is to take a moment about point B. It's quite good to take a moment about point B because there are lots of forces acting at B, and the good way of cancelling them all out is just by taking a moment at that point. So the first thing we're going to do then is we're going to work out the anti-clockwise moments and the clockwise moments. So we're going to have L/2 times by mg. That's going to be going in the anti-clockwise direction, and we're going to have that equal to L times by t, and then it's going to be we want this component of it here, so that's going to be sine alpha, so it's t sine alpha. Okay, so that's the equation that we make there. We're going to cancel out L's from both sides. We're going to turn sine alpha into 5/13, so it's going to be t times 5/13 equals a half mg. And then timesing 13 up to the other side, dividing by 5, we're going to get 13/10 mg, and that's the value for t. Lovely. Next part here is to calculate the coefficient of friction between the rod and the plane. So what we're going to do here is to use both strategies of resolving horizontally and vertically, work out what R and friction are, and then do friction divided by R. So remember here that the way we can work out the coefficient of friction is by taking friction equals mu R and dividing it by R. So it's going to be friction divided by mu. So friction divided by R is mu. Now what we're going to have to do now is resolve vertically to get the friction value, and then resolve horizontally to get the R value. So in this case, resolving vertically, we're going to have mg going downwards, and we're going to have t sine alpha going upwards, and we're going to have plus F friction as the force going upwards. Now we know that sine alpha is 5/3, and we know that t is 13/10 mg. So this is going to be 13/10 mg times by 5/13. So that's going to be cancel, plus friction on this side, mg on this side. So we're going to have half mg on this side. Taking that onto the other side, we get half mg on this side. So friction here is equivalent to a half mg. Resolving horizontally now we're going to work out the value for R, And in this case, it's going to be R is the force acting to the left, and the force acting to the right is going to be T cos alpha, because that's going to be the adjacent side of this right-angled triangle here. That's going to be 12 over 13, so R is going to equal 13 over 10 mg, that's the value for tension, times by 12 over 13, cancel, 6 over 5 mg is the value for R there. So now what we'll do is we'll do friction divided by R, that's the value for mu, and in this case here, friction is going to be a half mg, R is going to be 6 over 5 mg, cancel, and it's going to be a half times by 5 over 6, so that's going to be 5 out of 12. Lovely, so there we are, that's the value of the coefficient of friction there. So yeah, that's how we do these, what I call drawbridge type problems. You can imagine that the bridge is the plank along the bottom there, and the string here there is the string that lowers the drawbridge down. So these are the types of questions I call drawbridge type problems. So there aren't many of these in the textbook, so what I've done in the description of the video, I've put a document with about 11 questions on it and their mark schemes, so you can have lots and lots of practice at these drawbridge type problems. We saw one in June 2018, that was the question that we've just seen previously, and I'm sure there'll be more come up in the future. So just to be extra prepared, we've got a few more questions in extra to the textbook in the description of this video. Lovely, thanks very much for watching.